This is the first video in a series of videos about confidence intervals. This is a topic that we've been building up to for quite a while. Um, the topics of sampling distribution, standard error, and margin of error have all been leading up to this topic. In this video, or in this topic, we'll learn how to reach a conclusion about a population, like the Bay Area, for example, and also say how confident we are about our conclusion. And toward the beginning of the semester, we learned about the idea of statistical inference. Statistical inference is when you reach a conclusion about a population and you're not 100% sure about your conclusion, but you do have a certain level of confidence about your conclusion. In this topic, we'll learn how to actually do statistical inference with a set of data. So what is a confidence interval? A confidence interval is a range of values that's calculated as an estimate of a population parameter. And I know this definition sounds pretty technical, so let's try to break down some of the vocabulary. A population parameter is basically a population statistic. It's a statistic that describes an entire population. So the mean age of the Bay Area is a population parameter. The mean GPA of US college students is another population parameter. A population mean, a population median, or a population standard deviation are all examples of population parameters. And we know that an interval is a range of values. So when I'm using the word range in this context, I'm not talking about the statistic that's called the range that we learned early on. I'm talking about a span of numbers that goes from a low end to a high end. So let's say 9 p.m. to 10 p.m. is an example of a range. That's the kind of range I'm talking about in this context. So when you create a confidence interval, what you do is you take a set of data from a sample and you create an interval or a range of values, and then you say how confident you are that a certain population parameter is within that interval. So let's look at an actual or just a made up example of a confidence interval. So if a person says, I'm 95% confident that the mean age of Pleasant Hill is between 33 and 37, that would be a confidence interval. A person is creating an interval, which in this case goes from 33 to 37, and the person is saying how confident he or she is that this population parameter, the mean age of Pleasant Hill, is within that interval. Another example of a confidence interval might be I'm 95% confident that the mean GPA of the US college student population is between 2.5 and 3.5. So you might be wondering where these two endpoints come from. They're actually calculated with a formula. When you create a confidence interval, what you do is you take your data set and you use the data set to calculate these two endpoints, and then you state your conclusion and you say how confident you are that the population parameter that you're interested in is within the interval. So here are the steps to create a confidence interval. These are the steps we'll be following in the examples we do in our class. You take a random sample of the population that you're interested in. You collect a set of data. The type of data that you collect depends on what you're trying to reach a conclusion about. So if you wanted to reach a conclusion about the mean age of Pleasant Hill, you would obviously take a sample of Pleasant Hill and record the ages of the people in your sample. Or if you wanted to reach a conclusion about the mean GPA of US college students, you would take a random sample of US college students and record the GPAs of the people in your sample. Next, you calculate a sample statistic, which is just a statistic that's calculated with a sample. And then you also calculate a margin of error using the formula we've already learned. Then what you do is you take your sample statistic and you add and subtract the margin of error. And this fifth step is what leads to your confidence interval. So to get a confidence interval, you take your sample statistic and you add and subtract the margin of error, and you get two answers, and those two answers are the endpoints of your confidence interval. If you already understand the margin of error, then a confidence interval is really just one step further. You might You might have realized how in this class, each topic builds on the last topic. In this case, this topic of the confidence interval is really just one step beyond the margin of error. So here's a diagram of what a confidence interval looks like after it's already created. I said that to create a confidence interval, you take a sample statistic and you add and subtract the margin of error and you get two endpoints. Since you're adding and subtracting the same number from the sample statistic, you get two endpoints that are the same distance from the sample statistic. This point and this point are the same distance from the sample statistic, and the sample statistic ends up right at the center of the confidence interval. So here's some examples of different confidence levels. So when a person creates a confidence interval, the person actually chooses how confident they're going to be in their conclusion. If I'm creating a confidence interval, I might decide that I want to be 20% confident in my conclusion. I might decide that I want to be 20% confident that the population parameter is inside the interval. Or I might want to be 50% confident, or I might want to be 95% confident. Now, 95% confidence is what people typically aim for when they're creating a confidence interval. In almost all cases, the goal is to be 95% confident, but if I wanted to, I could set the confidence level lower and decide I'm only going to be 50% confident or only 20% confident. It's possible to do that in theory. So now let's go over, well, first, let's talk about how let's talk about where the confidence level comes from. So if you want to be 20% confident, what you do is you take your sample statistic, you calculate the 20% margin of error, and then you add and subtract the 20% margin of error. If you want to be 50% confident, what you do is you calculate the 50% margin of error, and then you take your sample statistic and you add and subtract the 50% margin of error, and you get your 50% confidence interval. So basically the confidence level comes from the margin of error that you're calculating. And in the last topic, we learned how to set the confidence level for a margin of error, right? If you want the 95% margin of error, you plug in 1.96, right? If you want the 50% margin of error, it's a different z-score. So in all the examples that we'll be doing in these videos, we'll be creating 95% confidence intervals, since that's what's most common. So what we're going to be doing is calculating the 95% margin of error using 1.96. Then we're going to be adding and subtracting to get our 95% confidence interval. So now let's look at the formulas that are used to calculate a confidence interval. I said that a confidence interval is a sample statistic plus or minus a margin of error, but that's just a generic formula that applies to all situations. These are the formulas for specific situations. And there's actually three situations that we'll be focusing on in our class. The first situation is creating a confidence interval for a sample mean when the population standard deviation is known. So what you do in this situation is you calculate a sample mean, which is x bar. You calculate the margin of error for a sample mean, and then you take your sample mean and you add and subtract the margin of error, and you get two answers. Now, the second situation is creating a confidence interval for a sample proportion. So in this situation, what you do is you calculate a sample proportion with your data set, which is p hat. X bar is sample mean, p hat is sample proportion. Then you calculate the margin of error for your proportion, which is using this formula. Then you add and subtract to get your interval. And all of the symbols that are in these two formulas are symbols that we've seen before. We know x bar is sample mean. We know p hat is sample proportion. We know that this is the margin of error for a sample mean. We know that this is the margin of error for a sample proportion. But the third situation actually has some symbols that we haven't seen before, and I'll explain what those are. So the third situation that we'll get to is creating a confidence interval for a mean when the population standard deviation is not known. In all of the examples we've covered so far in these videos, the population standard deviation has always been known and it's always been provided. And I've never really gone into too much detail about how we know what it equals. I've always just been saying that we somehow know what it equals and it's been provided. But and when you're doing an actual survey, the population standard deviation is not going to be known. And you'll have to deal with that in an actual survey, and you would end up using this formula in this third situation. So if the population standard deviation is unknown, the z-score for the margin of error is replaced by something called a t-score, and the t-score is really just an adjusted version of the z-score. And we know that when you're calculating a 95% margin of error using z, the z is 1.96. And in this third situation, you take that 1.96 and you adjust it upward by a certain amount. So t ends up being something higher than 1.96. Now the amount that you have to adjust it upward by actually depends on your sample size. If the sample size is small, you need more of an adjustment because the small sample size is likely to have a greater impact on your results because of the loss of accuracy. And what you do here is you take the population standard deviation and replace it with a sample standard deviation. So when the population standard deviation is unknown, what you do is you actually take your data and calculate a sample standard deviation using your collected data. And sample standard deviation is the letter S. And n is still n. So what we're doing here is we know that substituting the sample standard deviation for the population standard deviation is going to throw off the interval by a certain amount, right? Whenever you make a substitution, it's going to throw off your result at least a little bit because the sample standard deviation isn't the same thing as the population standard deviation. So you have to attempt to correct for that substitution to bring the results back where they should be. And the adjustment that you do for that is the t-score. So the t-score is really just an adjustment that's done to correct for the fact that we're making this substitution right here. And now let's go into one example of creating a 95% confidence interval. This is going to be an example of situation 1 in which we're calculating a mean and the population standard deviation is known. So here we have a mean age of a population which is unknown. We're doing a survey because we would like to estimate it, but we don't know what it is. That's our population parameter that we care about. The population standard deviation is actually known. We know that it's 10.8, and somehow it's been provided to us. And we take a random sample of 45 people, we record their 45 ages right here, and in part A, we want to know what does the sample mean equal. To get the sample mean, we take our 45 values, the ages, and we add them and divide by 45. That gives us the mean of the data set, and it's 39.8. In part B, we have to know if a margin of error can be calculated. So we have to use our checklist that we've been using for when a sample mean is being calculated. In the earlier videos that I did for margin of error, this was phrased differently. I said, is the sampling distribution at least roughly normal? And when I said, is the sampling distribution at least roughly normal? What I was basically asking is, can a margin of error be calculated? Because the sampling distribution has to be roughly normal for the margin of error to be solvable. So it's just two ways of saying the same thing. Just here I decided to phrase it the other way. So we take our checklist. I said that when a mean is being calculated, this checklist tells you if the sampling distribution is at least roughly normal. And we don't have, the population is skewed, the ages are skewed right here, so this is not true, but the sample size is 30 or larger, and that checks off. And you might remember that only one of them has to check off for us to go forward. So now let's calculate our 95% margin of error. We get our z-score from the table, it's 1.96. We plug in our population standard deviation, which is 10.8, and our sample size of 45, because it's 45 people. The square root of 45 is 6.71. We divide 10.8 by 6.71. Then we multiply by 1.96 and we get our answer. It's 3.16. That's the 95% margin of error. Next, what we do is we just go one step further. We take our sample mean, which is 39.8. Remember that 39.8 was our answer to part A. It's the mean of the data set. And we add and subtract our 95% margin of error, which came from part C. So it's sample mean plus and minus 95% margin of error. When we subtract, we get this answer. When we add, we get this answer. And we get two answers. These are the two endpoints of our 95% confidence interval. And now we just have to reach our conclusion. When you reach a conclusion in this type of problem, it's always, well, at least in my videos, it's always going to be phrased in this type of a way. So we're just going to say that we're 95% confident that the population parameter that we care about is between here and here. In this specific problem, what we say is, I'm 95% confident that the mean age of the population is between the lower number and the upper number. And the reason why I'm saying mean age of the population is because that's what we're focusing on in this example. In this situation, the mean age of the population is what we care about. It's what we want to estimate. We would like to know what it equals. So that's what we put into our sentence at the end of the problem. Now, if we were interested in the mean GPA of the population, then we would just say mean GPA of the population is between here and here. So you just have to phrase it in the context of the situation that you're dealing with. Now let's create a confidence interval for a proportion. So in this situation, there's a population, and we would like to know the proportion of this population that's students. Remember that a proportion is just a percentage written as a decimal. So if 45% of this population is student, then that would mean that the proportion is 0.45, right? But in this situation, we don't know what this proportion equals, and we're going to do a survey, or we're going to imagine that someone is doing a survey to try to get an idea of what this equals. So this person takes a random sample of 100. They ask each person, are you a student? And each person gives a yes or no answer. And we're imagining that this person doing the survey ended up with this data set, 18 yeses and 82 nos out of 100 people. First, we want to know what the sample proportion equals, because the sample proportion is what gives us an estimate of the population proportion, which is what we care about. So 18 out of 100 people means that 18% of the sample said that they are a student. So now what we need to know is, can a margin of error be calculated? Well, remember that when a proportion is being calculated, you have a different checklist, right? We have to know if n times p, or in this case p hat, is 10 or larger, and n times 1 minus p hat is 10 or larger. And I forgot to put the extra line down here, but it should be there because what I'm actually meaning is 10 or larger, not above 10. So there should be a greater than or equal sign right here. So let's try this. Our sample size of 100 times the p of 0.18 is 18. The sample size of 100 times 1 minus p, which is 0.92, equals 92. So n times p is 18, n times 1 minus p is 92. They're both 10 or larger, right? This is above 10, 18 is above 10, 92 is also above 10. So this checks off, that checks off, and the answer is a yes. It can be calculated. Remember that in this situation, both of them have to check off. That's why the word and is here rather than the word or. So yes, it can be calculated. Now let's calculate our 95% margin of error. So what we do is we get our z-score for 95%, which is 1.96 from the table. We take the proportion, which in this case is 0.18, and plug it in here. And we plug in our sample size of 100, and we have everything we need. 1.96 times the square root of 0.18 times 1 minus 0.18 over 100. And we just solve. We subtract inside the parentheses. 1 minus 0.18 is 0.82. 18 times 0.82 is 0.15. 0.15 divided by 100 is 0.0015. And then 1.96 times the square root of this is 0.08. So that's 0.08 is the 95% margin of error. Now we can get our confidence interval because we just have to take our sample statistic and add and subtract our 95% margin of error. Our sample statistic is the proportion from part A, the 0.18. Remember, 18% of our sample said that they're a student. And this margin of error came from part C. So 0.18 plus or minus 0.08 equals 0.10 and 0.18. Now we have our interval, and we just say that we're 95% confident that the population is somewhere between 10% and 18% student, and we write the two percentages as decimals because they're proportions. And then we're done. So now we've covered an example for a mean and then an example for a proportion, and they all work the same way, right? We first, in part A, we calculate a sample statistic. In part B, we do our checklist. The checklist that you use depends on if it's a mean or if it's a proportion. There's two checklists. Then we calculate a margin of error using the correct formula, right? There's a formula for a mean and a formula for a proportion. And then we just, in part D, we take our sample statistic from part A, and we add and subtract our margin of error from part C, and we get our two answers. Then we just write the conclusion at the end. And it's always phrased in this type of a way, at least in my videos. And there's one thing I wanted to mention before we end this video. So you might remember that in the formula for the margin of error for a proportion, I used to say just p, right, and not p hat. So you might be wondering where this p hat is coming from and why it's not just p. Well, in the examples that we did in the margin of error topic, we knew what the population proportion equaled, right? Well, in each of the examples that I gave you, I would actually tell you what the population proportion equals, and it would be provided, and you would plug that in, right? And it would be a population proportion. But now, in a confidence interval problem, we don't know what the population proportion equals. It's not provided, because when you create a confidence interval, the whole point of it is to try to reach a conclusion about the proportion, right? If it was known, then why even bother with this procedure? So what you do is, since it's not provided, you calculate a proportion using your sample, and you calculate a sample proportion, and sample proportion is p hat. So basically, p is not known, so you calculate p hat and you plug it in as a substitute. It's the next best thing, right? That's really all I'm saying here. If you don't know p, p hat is the next best thing. And this is really in any situation in which you need to know a population, a parameter for a formula, and you don't actually know it, what you do is you calculate the sample statistic, the sample version of it, and you use it as a substitute. That's a standard procedure.